Hello everyone. Our our topic for our report is all about the steady state errors, which is found in Chapter 7 of Control Systems Engineering by Norman S. Neese, reported by Taclayan Jose Ignacio, Luna John Rome, Galeniano Bin Vincent, Buendia Bon Anthony, Amantiad R.J. We will talk about two subtopics for this report. So the first topic will be all about steady state error for unity feedback systems. So steady state error is the difference between the input and the output for prescribed test input as time reaches to infinity. So what this means is that the steady state error or the error function of any in a example for a block diagram is just equals to the input minus the output, in which time goes to infinity. As you can see in the table below, which is in waveform named physical interpretation time function Laplace transform. In the first line, we have a waveform of a straight line, which is called a step. So in step, there will be a constant art output function. So in ramp and parabola, it's for ramp, it's a straight line going to infinity, while parabola is like exponential growth. For this topic, we need to refer to this block diagram, in which we have an input function of Rs and an output of Cs. So we need to remember this because our formulas and equations are based mostly on these functions, which is the output. In this case, it is Cs, and the input, which is the Rs. So both block diagram A and B are just similar. It's just that inside the box, in the function box of B, there's a Laplace transform there. What this means uh, is that there is a time function in block diagram B. So the most common of these two is this function ES. So this ES means this is the error step function, or simply put, the steady state error function. And I can see in the box below that the error of a steady state is equals to the 1 over k to the output of steady state. So it's just the 1 over k here means that it's just a constant of error. So in this slide, you can see a bunch of equations and formulas. So these are the formulas for steady state errors in TS. So TS means here is that the function or block diagram has no feedback on it. So it's just a linear block diagram. So this all of these equations are just similarly to each other. It's just that the fundamental equation, which is the steady state error ES, is equals to Rs minus Cs. So simply put, the error, which is E, is equals to the input minus the output. So error is just input minus output. And in the next equation, the output is equals to the input times the TS function, which is just similar to a block diagram. If we substitute this equation through here, we will get the final equation, which is that the steady state error is equals to Rs multiplied by 1 minus Ts. So this is just the formula we need to remember always, which is which is error is equals to the input multiplied by 1 minus Ts. So keep in check. The most important formulas we need to remember is just these two, 7.2 and 7.4. These two are just similar to each other. So in this slide, it is taught that if we derive the functions, for example, the e infinity is equals to the limit of e if the time function as t approaches infinity, we can find its Laplace is equals to the limit is equals to the Laplace SES, since this came from a derivative, as s approaches to 0. So if you plug this equation from before, from the equation 7.4, we can find the Laplace of that, and we just plug it here in the new equation, which is 7.6, which is that as the error goes to infinity is equals to the limit as s approaches to 0 is equals to s times rs multiplied by 1 minus ts. So see, the two equations from the previous slide and this equation are just similarly to each other. It's just that the previous equation was just transformed. So lastly is the formulas and equations of steady state error in the GS form. So GS, what this means is just the function has just a feedback. So it's just similar to the TS, but this time we just have a feedback on our block diagram. So the first equation is just the same, which is the error is equals to the input minus the output. But this time the output is now multiplied by the error and then the GS function. These two are just similar, and if we substitute 7.9 to here, we will reach another new equation, the fundamental equation, which is the error is now equals to the RS over 1 plus GS. So this is just like the in chapter 5, which is a parallel block diagram. Now, if we also find its derivative of its Laplace, we will also find its Laplace transform in 7.11, which is just the error as it reaches infinity is that the limit as s approaches to 0 is SRS and 1 plus GS.
Now we will be solving example 7.1, which is about steady-state error in terms of T of S. We are asked to find for the steady-state error. We were given a transfer function which is 5 over s squared plus 7s plus 10, and an input which is a unit step which is 1 over s. In order to solve this, first, we know that the transfer function is output over the input. And if we isolate the output, we get the transfer function multiplied by the input, which we will call equation 1. And we had discussed that the error is input minus the output, which we will call equation 2. And if we substitute equation 1 to equation 2, we get r of s minus t of s multiplied by the r of s. And we factor out the input, we get r of s multiplied by the quantity of 1 minus t of s, which we will call equation 3. And if we substitute the transfer function and the input into equation 3, we get s squared plus 7s plus 5 over s multiplied by the quantity of s squared plus 7s plus 10, which we will call equation 4. We then use the final value theorem to find the error, which is limit of s multiplied by the e of s as s approaches to 0. And if we substitute equation 4, we get this. We can see that both s's will be cancelled, and as s approaches to 0, we can cancel all the s's and replace them to 0. We will be left with a numerator of 5 and a denominator of 10. We then get that the error is equals to 1/2 or 0.5. Now let's take a look at an example about steady-state error in G of S. The problem is to find the steady-state errors for inputs 5p of t, 5t of t, and 5t squared u of t to the system shown in figure 7.5. First, let's find the steady-state error for the input 5u of t. When you take the Laplace transform of the input, you get 5 over s. And this input is a step input. So we can find the steady-state error using equation 7.11 in Normalized book, which is the limit of s multiplied by r of s over 1 plus g of s as s approaches to 0. And the g of s on this system is 120 multiplied by the quantity of s plus 2 over the quantity of s plus 3 multiplied by the quantity of s plus 4. So when substituting r of s and g of s into the equation, we get this. We then can get rid of the s's, which will then give us an error of 5 over 21. Now we will solve for the steady state error for input 5t of t. So when we take the Laplace transform, we can get 5 over s squared, which is a ramp input. So we will still be using equation 7.11 for finding the steady state error. So when substituting the input into the equation, we get this. So as you can see, not all s's from the input have been cancelled. So what this does is when s approaches to 0, the whole denominator becomes 0. So this will give us an error of infinity. So now for the input of 5t squared u of t, when we take the Laplace transform, we get a 5 over s cubed, which is a parabolic input. So for this, we will use equation 7.20, which is 1 over limit of s squared g of s as s approaches to 0. Substituting the input and the g of s into the equation gives us this. And as you can see, this will still make the denominator 0, which will still then give us an error of infinity.
So the next topic we are going to discuss is static error constants and system type. Static error constants. So we can see here for a step input ut, so we could get E infinite is equal to E step infinite equals to 1 over 1 plus limit gs as s goes to 0. So for ramp input tut, so E infinite is equal to E ramp infinite is equal to 1 over limit sgs as s goes to 0. For a parabolic input, 1 half t squared ut can get infinite is equal to E parabola infinite equals to 1 over limit s squared gs s goes to 0. So we could use this later for solving static error constants in the problem. So the next is if we're going to find the position constant, we could use Kp is equal to limit Gs as S goes to 0. So if we're going to find velocity constant, represent as Kv, use Kv is equal to limit Sgs as S goes to 0. And if we're going to look for acceleration constant, which represents Ka, could use Ka is equal to limit s squared gs as s goes to 0. So to summarize this equation, so if we're going to get the step input, so Es or error s is equal to 1 over 1 plus Kp or the position constant. If we're going to find the ramp input, so could use Ev is equal to 1 over the velocity constant. And finally, if we're going to look for the parabolic input, so we could use EA is equal to 1 over acceleration constant.
Hey guys, Robin here. So for this example, for the steady state error via static error constants, for each system of the figure shown below, evaluate the static error constants and find the expected error for the standard step, ramp, and parabolic inputs. So for this case, since we are given this problem, we need to identify what we need to solve. So what do we need to solve? First are the constants, Kp for the step, Kv for the ramp, and Ka for the parabolic. Next, we need to solve for the errors. And these errors are specific formulas. For this is as shown here, these are the formulas. So with this, we know what to solve, but we have to identify what we are given. So in this case, our given is g of s is equal to 500 times s plus 2 times s plus 5 over s plus 8 times s plus 10 over s plus 12. So there is, as discussed earlier by my group mates, there is a process and we need to follow that process to have a proper answer. So with this, since we know already what we need to solve, since in solving the constant, there is also very specific formulas for this, especially using limits. So in this case, for the step input, it is the limit of g of s as s approaches 0. For ramp, it is the limit of sgs as s approaches to 0, and for parabolic, it is the limit of s squared gs as s approaches to 0. Since we know these formulas, we just need to apply this to our given g of s. So for the step, ramp, and parabolic, for this step input, so we know that kp is equal to limit of g of s as s approaches to 0. Simply replace g of s with the given function. So with that, what we need to do, since we're in limits, we just need to evaluate by erasing this s and basically turning them to zeros and solving for kp. So in this case, kp will be equal to 5.208. For ramp, on the other hand, same process but with the additional s, just multiply it with s. But since s approaches to 0, it becomes automatically 0, as well as for the parabolic. So basically, kp is 5.208. This is kb is equals to 0 and ka is equals to 0. Since we have our kp's, we simply need to substitute it for its specific formula. For the errors, on the other hand, since es is equals to 1 over 1 plus kp, simply substitute for kp. So since it's 5.208, basically the error is 0.1611 or 16.11%. For ramp, on the other hand, since we're dealing with limits, it does not mean it becomes 0. Basically, it becomes infinity. The error is infinity, as well as for the parabolic. So, since in this problem, this is basically a step input problem, their cases vary depending on the types you are solving. So, it will be discussed later by my group mates again. As for the types and how to solve it, or basically he will say the summary, and later we will solve for the errors or solving for case and identifying and evaluating these types of problems.
Hello guys, my name is John Luna and I'll be talking about the different system types. So, considering this figure of a system, we have a function of g of s equivalent to k multiplied by the quantity s plus z1 and s plus z2 and so on, and all over s to the power of n multiplied by the quantity s plus p1, s plus p2 and so on. So we can define, with this we can define system type to be the value of the exponent n here in the denominator. We could call this as the number of pure integrations. So this means that if n is equivalent to 0, we could call this system a type 0 system. So if n is equivalent to 1 or 2, this system will also be called as a type 1 or type 2 system. So for example, this system right here, as you can see, there's no s here. So as we all know, s to the power of 0 or any number or any variable raised by the power of 0, it will automatically be equal to 1. So the imaginary one here, we can assume that it is equal to s to the power of 0, and therefore we can call this system as a type 0 system. So in this system, we have an s here with an imaginary exponent 1. Therefore, the system is going to be called as type 1 system. So lastly, the system has an s squared in the denominator. Therefore, we can call this a type 2 system. So for a summary of the topics that we've encountered so far, the relationships between input, system type, static error constants, and steady state errors. We have here the different kinds of inputs, the steady state error formulas, and also the type 0, type 1, and type 2 systems and their corresponding static error constants errors. So for step input, you have a steady state error formula of 1 over 1 plus Kp, in which Kp, or the position constant, is equivalent to the limit of g of s as s approaches to 0. So for a type 0 system, the equivalent static error constant will be a constant. So to recall, we'll have this representation or example. So as we all know, Kp is equals to the limit of the g of s, for in this case, this is the g of s as s approaches to 0. So as mentioned earlier, type 0 systems are those with without s here, those with um, those s to the power of 0. So you can say that this is a type 0 system, and if we evaluate this, all s's are cancelled out or will be equivalent to zeros, and all that's left will be constant, and the result will be also be equivalent to a constant. And so for the equivalent error, you just substitute Kp to the standard state error formula, steady state error formula rather. So 1 over 1 plus Kp, the resulting constant number. So the error result also will be a constant. So for a type 1 system, the equivalent static error constant I step for step input, it will be equivalent to infinity. So for a representation also, so as we all know, a type 1 system has an s as in their denominator with an exponent of 1. So as we evaluate this, we'll if we limit this s, it will become 0, and it will make the all denominator be equal to 0. So the resulting constant would be the resulting for this equation will be equal to infinity. And so the equivalent error value, so you just substitute also again the Kp into the steady state error formula here. So 1 over 1 plus Kp, or 1 plus infinity, it will become 0. So for the type 2 systems, standard error constant will also be equal to infinity. So as we all know, a type 2 system has an s squared here. So if we evaluate this s squared will also be equal to 0, which makes the whole denominator 0. And so Kp will be equivalent to infinity, and also the error value will also be 0, as because the Kp is equivalent to infinity also. So for the ramp input, um, we have a steady state error formula of 1 over Kv. So, and Kv is equivalent to the limit of g of s as s approaches to 0. So for type 0 systems, their ramp static error constant equivalents are 0. So to better understand, so type 0 systems, no s here, so that means their the number of pure integrations are 0. So, and as we all know, Kv is equals to the limit of g of s as s approaches to 0. So if we evaluate this s will also become 0, and therefore multiplied to the function, the whole equation becomes 0. And to get the error value, you should just substitute this to 1 over kv, in which 1 over 0 and it will be equivalent to infinity. So the error value of a type 0 system in terms of the ramp input, it will be equivalent to infinity. So for type 1 systems, their static error constant will be equivalent to a constant for the ramp input. So here, we all know type 1 systems have an s here with exponent of 1 in their denominator. So as we can see, we can cancel out these s's. So the remaining function will just these ones without the s's here, just these two s. So if we evaluate this whole as a limit, we could come up with a constant. So getting the error value, you just substitute this constant. So 1 over kv, or 1 over a constant, the resulting will also be a constant. So for type 2 systems, the static error constant for ramp input will also be equal to infinity. So type 2 systems have s squared in the denominator. So cancelling this out, there will be an s here that will remain with an exponent of 1. So if we evaluate this remaining s here, uh, this remaining s here will become 0 as we evaluate this. So if it becomes 0, the whole denominator will become 0, and the resulting will be infinite. So the error value will also be 1 over infinity is equivalent to 0. So for the parabola input, for type, you have a steady state error formula of 1 over ka, where ka is equivalent to the limit of s squared g of s as s approaches to 0. So for type 0 systems, we have the static error constant for parabola input of equivalent to 0. So why is this? So as we all know, type 0, no s here, just an exponent of 1 or imaginary 1 here. So, and ka is equal to the limit of s squared of g of s. Therefore, if we evaluate this um, s squared here will become 0. If we evaluate this in terms of limits, so this will become 0, and multiplied by it to the function, the whole equation will become 0. And for its error value, we'll have 1 over ka. So ka is 0, so 1 over 0, it will be equivalent to infinity. So for type 1 systems, we have the static error constant also be equivalent to 0. So here, we'll have this for type 1 systems, 1s here. So to s squared divided by s, this will cancel, and this will become 1. And if we evaluate this in through limits, this will become 0, and if multiplied to the function, the whole equation becomes a 0, equivalent to 0. So for the error, it goes the same, it will become infinity. So for type 2 systems, the static error constant for a parabola input is equal to a constant. So type 2 systems, s squared in the denominator, and ka have s squared also here also. So this 2 will be cancelled out, and if we evaluate this through limits, we get a result of a constant. And if we get the error value 1 over a constant, the whole or the resulting answer would also be a constant. So thank you.
Since we already know how to identify the types and how to solve for its respective constants and errors, now let us go to a new problem. So the problem is, given the control system in the figure, find the value of k so that there will be a 10% error in the steady state. So in this problem, just like before, we need to identify what we need to solve. So what to solve? K, and our given would be this, the GS. And with the GS or the function, we can identify what type it is as discussed earlier. So basically, this is a type 1. So if it is a type 1, automatically, we would use the ramp input formulas. So basically, E is equals to 1 over KV, or basically equal to 1 over the limit of SGS is equals to 0.10. So with that, since we know the values of, we have the error values, basically what we're lacking is the constant. With that, we simply apply the same concept in solving. So with this, you just need to set this to 0 as all s to 0, cancel this s, and basically you will end up with this. It is a then it will be a matter of algebra or basic algebra, and you would end up with an answer of 672. So another example is on the skill assessment exercise 7.3. A unity feedback system has the following forward transfer function. So in this case, since g of s is already given and we have an error of 10%, we can automatically do the same process as earlier. So what to solve? Still k with a given gs, and with a given gs, we can automatically identify this is a type 0. So our error formula will be E is equals to 1 over 1 plus Kp equals to 0.10, since it is 10% error. So with that, the same process, 0.10 is equals to 1 over 1 plus the limit of g of s as s approaches to 0. Simply substitute g of s earlier is after substituting, apply the same concept, turn them to 0, or assume to 0 all s and solve. So with that, it is a matter of algebra, basic algebra, and you will get the answer of 189.